Welcome. In this video, we are going to implement the great Pix2pix paper. So as the title suggests, so image-to-image translation with CGAN. The aim is to do image-to-image translation. For example, transform images to pictures, do, for example, day to night, labels to facade. That was an interesting research paper. And since its release 6 years ago, there have been a lot of use cases in the industry, a lot of improvements. For now, let's focus on this foundational paper. Very interesting and very useful. So these are the results we get by the end of this video. We are going to focus on facade, from labels to facade. So you can see some kind of input and some kind of output generated by the model. I think results are very good, on par with what is shown on the paper. Okay, so let's dive into the implementation. As always, we're going to use PyTorch for the implementation. We can start by implementing the neural network architecture. So basically, the generator is a UNet. So basically, it's based on first we downsample the image, then with a middle block, and then with an upsampling block. Okay, so an upsampling branch. So first we need to implement downconf blocks, so blocks to downsample the image, and we are going to put them we are going to combine many of them to create the downsampling part of the neural network. So basically that's a simple combination of activation function, convolution, batch normalization. For the convolution, we are using a stride of 2 so that it will downsample the spatial resolution of the image. And then with the fourth pass, we just straightforward implementation. We just give the input X to the block. Okay, we've implemented the downconf block. Now we can do the opposite. Implement the upconf block for upsampling back the image in the upsampling part of the unit. So basically, same with combination of activation function, convolution layer on batch normalization. So here we're using the convolution transpose 2D for upsampling, and again a stride of 2 for a time 2 upsampling. We will also give the possibility to add dropout to those layers. So there is a flag dropout, and by default we're using dropout with a 50% probability. Okay, and then we just create the block out of all those layers, and then we can implement the fourth pass. We just give the input X to the block. Okay, so now we can implement our unit. So basically we can combine those blocks to create a full unit. We are going to implement a unit with a skip connection. So the first thing to do is to project the image into, we are going to project the image into, to project the 3 channel to more channel, so that then we can feed them to the, the most interesting part of the unit. So basically at the beginning with a convolution just for projecting the image into a higher number of channel. On the other end, we will do the opposite. We'll have a conv out to go from the output number of channel from the last upconf block, and to project that back to an image of 3 channel. Okay, so now that it's done, we can implement our downsampling part. So a sequence of 6 downsampling blocks. And basically, you see that we, to some extent, we are always increasing the number of channel. So basically, we are trading spatial resolution for number of channel. We want to keep as much information as possible. So we are not, on one side we are downsampling the spatial resolution, but on the other side we are increasing the number of channel. And that allows to keep, not to destroy too much information, okay? Because if we just downsample the spatial resolution, we lose information, we lose the total number of units that encode information. Okay, so with our downsampling blocks, then we have the middle block. So here that's just a sequence of activation functions, convolution, batch normalization, and then we can implement the upsampling block. So now we go from, we do the opposite, we reduce the channel size, but we increase the spatial resolution. We use dropout for the first layers, and then we do not use it. And you can see that here we are using 1024 channel, although the output of the middle block is 512. So we have twice as many channel, but that's because we implement skip connection. Maybe very briefly, we can have a look at that in the paper. Basically, every upsampling layer receives the input from the previous layer, but also the output from the mirrored down sampling block. Okay, and that's very important. They make some ablation studies. They have some figures with some ablation studies, and here that's pretty important to have this architecture. Okay, I'm not sure what this is. I invite you to have a look at the paper, but yeah, this is crucial. That allows to return high-level information. Well, I mean the fine details. Okay, well, now we can implement the outermost layer. So to go back from the 164 or 64 plus 64, because again, with the skip connection, so 128 channels towards 3 channels. And then we can implement the fault path. We could have generalized the code. There are a much better way to generalize the code. For example, having a single down block in a nn.sequential, same for up. But as the aim of this code is to be educational and to be easy to understand and to read, I prefer to implement it like this, so that there are ways much more elegant and much shorter to write it. But I think this is very easy to understand. So I prefer to write it like this. Okay, and here you can clearly see the skip connection. Here you give the previous output, but you also feed x6, and you do the same for all the x's. So you implement the skip connection. Okay, so that's it for the unit. Now we can move on to the discriminator. So the unit is for the generator. For the discriminator, we implement the patch GAN, which means that we are not the discriminator does not have a look at the full image, but only discriminate patches in the image. They also study that in the paper. By default, they recommend to use patches of 70 by 70 pixels. Okay, so we create the neural network, a sequence of convolutions, activation function, batch normalization. So pretty standard. And once the network is implemented, then we can implement the fault path. On basically, maybe we can come back to that later, but we'll see that when we implement the training loop, what we give as input to the patch GAN is the full image, well, the fake image or the real image. We do not manually extract patches from the image ourselves. Basically, by design, this architecture is a patch. The receptive field of this neural network is 70 by 70 pixels. So that means that for each pixel, we have a receptive field of 70 by 70. So we're not going to have a look at the full image at once. By design, this architecture is acting like a patch GAN, only having a look at patches of 70 by 70 pixels. Basically, we are not going to have a single output when we forward an image that is high resolution. We are going to have many outputs. So basically, it's as if we are classifying each patch individually. Okay, now we can implement the dataset. So basically, we take as input a data path. We read, we search for all images with the extension JPEG, and then we are going to load those images later in the getItem function. We can prepare a transform list to a set of transforms to apply to our image. So when we read them, there will be a pillow image. Then we are going to transform them into PyTorch tensors, and then normalize the images. Okay, the length of the dataset is just the number of images. So very important when you implement a custom dataset in PyTorch is to implement the length function on the getItem function. So basically the getItem tells us for a given index, for a given image index, how we should read it. Okay, so here we with a 50% probability, we add a random horizontal flipping. So basically why we do this? So basically we want to randomly flip the images. But here I'm doing it here instead of adding it in my transform at the very beginning. The thing is, this will, as the name suggests, apply a random horizontal flipping. The issue is that I have two images, A and B. If I do a random flipping to A and a random flipping to B, I might flip one or not the other. And as these are input-output, a bit like supervised learning, we want those images to match right. If we flip one, we need to flip the other. Okay? You do image to image. If you do one augmentation to an image, you need to do the same to the other one. So here what we say either with a 50% probability, I will flip both images with a 100% probability. So I flip them both with a 100% probability, or I do not flip them at all. Okay, and that's why we need to do this kind of trick. Only with a 50% probability, we flip all images with a 100% probability. Okay, so basically here we load the images. In the way this dataset, so the one we use in our in this tutorial is so labeled to facade. They are on, the way those images are encoded in the dataset. Labels or images are on the same image. So basically that's a vertical image, well, horizontal image, sorry, where you have both image on the same, image on the same image. So we load AB, so that's a single image, and then we need to split the image in two, on the B part, on the A part, so input, output, and then we apply the transform to each image. So again, be very careful. That's a very common mistake in image-to-image translation. When you have, you need to be very careful if you have randomness in your transformation, then you want to apply the same transform to A and to B. Okay, so you always need to make sure to apply the exact same transform to A and B. Okay, so that being said, now we can move on to the most interesting part, implementing the algorithm by itself, so the training loop. So we get the generator, the discriminator, we get an optimizer for each of them, a scheduler for each of them, data loader, number of epoch, device on which we train. There is some, I don't know if you can call that a regularization, but there is the vanilla GAN loss. And on top of that, there is a geometric supervision. So we use the L1 loss. And basically, that's the weight of the L1 loss with respect to GAN loss. Okay, so by default 100, that's the value used in the paper. Basically the criterion for the L1 loss is just the L1 loss. But we could have used something else, for example, the L2 loss. But that means maybe we should generalize this term, not call it criterion L1, but something else. But okay, anyway, let's move on. Okay, so we iterate for a given number of epoch. We iterate over our data loader. So we read the images from the batch. So read image A, image B, or the batch of image A, batch of image B. If I recall correctly, by default we use a batch size of 1, so we only do one image at a time. Then basically now we have a standard GAN training, so we generate a fake image from the generator, and then basically we compute the vanilla GAN loss using the binary cross entropy. Here we're using the binary cross entropy loss with logits, so that allows to have results that are more numerically stable. I won't go into details of that, of the maths, but I have almost 20-hour course about GANs on Udemy. If you're interested, I will put the link in the description. Yeah, if you want to learn more about GANs, about more advanced topics. But okay, anyway, this is the vanilla GAN objective, okay, for the discriminator, and then we can train the generator. Here, that's the same with the vanilla GAN loss for the generator, and then on top of that, we use the L1 loss between the generated image and the real image, so we have some kind of supervised learning loss to ensure like geometric consistency between the input and the generated image. Okay, well then we can do one step of scheduling to decay the learning rate, and then we are almost ready to start training. First, we need to initialize the weights properly, so very important in machine learning to properly initialize the weights of neural networks. That's even more important when you have GANs. You need, sometimes training can be unstable. Of course, there are tricks to stabilize training. Again, I invite you to have a look at the description for more content about GANs. But okay, here we are making sure to properly initialize the weights as is described in the paper. And then we can put everything together, recreate the unit, the generator, recreate the discriminator. Again, for the discriminator, we are feeding, so netd, we are feeding the full images. I did not describe that, but we are also, the discriminator takes as input both the input real A on the generated image. So basically that was described in a conditional GAN paper. When you have a conditional GAN, you give both the conditioning on the generated image as input. But here basically, we feed the full image, right? We do not manually extract patches that we feed to the discriminator. By default, by design, the discriminator is acting like a patch GAN, only having a look at patches. So once we've created the neural networks, we can apply the weight initialization. We can create the optimizers, and then we can start training. Here we use some lambda rule. So basically, we are decaying the learning rate from 1 to, if I recall correctly, basically, for the 100 epoch, we keep the learning rate constant, and then for the last 100 epoch, we decay the learning rate from 1 to 0, well, from its value to 0, okay? So we implement that with that lambda rule that I've retrieved some code implementation that I've cited. And basically, we can feed this function in the learning scheduler lambda learning rate from PyTorch, and basically that will decay the learning rate using that formula. So basically that will, every epoch, that will multiply the learning rate by the output of this function, and basically the output of this function will be 1 for the 101st epoch, and then it will decay from 1 to 0. Okay, now that we have the schedulers, the optimizer, the knowledge works, we can create the data loader. It assumes that you have the data in the dataset facades train folder. Okay, again, we're using batch size of 1. That's what is described in the paper, or then you can start training. Once we're done with training, so we train with 200 epoch. So again, the first 100, the learning rate are fixed, and then they are decayed. And then we can put the model in evaluation mode and generate the results. So yeah, we create a test data loader to test on new images, new labels that have never been seen by the neural network. And then we create this image that you've already seen, input, ground truth, output. Okay, and then if you run this code, you save this figure, you will get a similar image to this one. I want to emphasize that there are very few images on this dataset. I don't know if you can see that in the paper. So what is very amazing about that paper is that even if you have only a few hundreds images, you get very nice results. Okay, anyway, I invite you to have a read at the paper. Yeah, I'm sure they describe that somewhere. Okay, but basically, yeah, they describe that with only a few hundred images for some of the dataset, you get very good results. I think for this facade to images, there are only a few hundred images, and you are able to go from those input to those output. Yeah, so very, very amazing. Of course, there were a lot of development since that release. I will cover that in my upcoming videos. So subscribe if you're interested to GANs and to machine learning in more general. I hope this video was helpful. If it was, please leave a thumbs up. It's really helpful. Comment this video and see you in the next video.